My name is Michelangelo D'Agostino, and I lead the data science team over at Civis Analytics. And today, I want to tell you all about Docker. In particular, I'm hoping by the end of the talk, I'll have convinced you to make Docker a regular part of your data science toolkit if it isn't already. But more than that, more than just trying to kind of argue this abstract point, I've really designed this talk to be more of a tutorial. So maybe you've heard about Docker, you've heard about containers over the last year or two, but you just haven't had time to dig in and figure out what they're all about. I've really designed this talk so that you can pretty much walk out of here knowing enough about the Docker toolchain, enough about the Docker syntax to just start using Docker as part of your data science work. But before we get into that, I just want to say a few things about kind of the rapid growth of Docker and kind of this age of rapid growth of tools that we're living in. So I think as data scientists, we live in this world of just rapid change to the landscape of tools that are available to us. It seems like every day there's a new package, a new framework, a new language, something that comes out. And I think that can cause us to have this sense of tool fatigue. You think like, hey, this new thing, is it really worth me investing my time and effort in learning it and understanding it? Or is it just some fad and something better is going to come along kind of in the next day or two? So I had this sort of fuzzy feeling that was the world that we're living in, but I didn't have any actual data to back that up. And as a data scientist, that bothers me. So I spent a little time last week with Google search trends to see if I could kind of quantify this a little bit. So let's start with deep learning. So if you've been reading Strata abstracts, you've been reading the news lately, if you've been anywhere not underneath a rock, you'll know about the rapid rise of interest in deep neural networks or deep learning. So, and how they're changing everything from image recognition to speech recognition to machine translation with all these new applications kind of popping up every day. And we really see that borne out in the Google search trends data. We have this kind of exponential growth over the last couple of years and interest around deep learning. Also, if you're reading Strata abstracts, you'll know about the rise of Spark as a distributed computing framework. And again, we see in the Google search trends data just kind of this rapid takeoff of interest in Spark. Now, of course, I'm not standing here at Strata Spark world giving this talk, right? At least not yet. This is still Strata Hadoop world. So I wanted to add the trace for Hadoop on here, and you pretty much see what you'd expect, that Hadoop took off earlier, it's reached much broader penetration, much broader interest, and has maybe kind of leveled off a little bit in the last couple of years. So I thought, all right, what can I add on here that's going to be even bigger than Hadoop, even more hyped than that? So I figured I would add, the big data industry on here. And I was a little surprised that it's not much higher interest than Hadoop. I think for some people they would argue that big data and data science are Hadoop. I don't think I'm one of those people, but maybe you look at this graph and you could make that argument. So given that sense that we have, that Spark's really taken off, deep learning has really taken off, I was still a little surprised to see what happened when I plotted the Docker trend line on here. So basically, Docker has eclipsed all of these things in terms of sheer volume of its interest, where it is right now, but also the rapidity with which it's arisen. So it's really, that purple curve is really just taking off like a rocket ship. And because of that, if you paid attention to Docker somewhere back here and you learned a little bit about the ecosystem, and then 4 months later you're over here, things have really changed rapidly. New tools come out, things change names, and it's sort of hard to know where you are. So basically, that's what this talk is for. It's basically all about explaining this purple curve. So I want to help you understand what is it that's driving this huge interest in Docker. A lot of which has been in the DevOps and systems community, but has kind of recently been breaking over into the data science world. And then to help you understand the current state of the tool chain, so that you can kind of walk out of here ready to just use Docker. But before I do that, I wanted to bring us back down to earth just a little bit, so that we don't think Docker's like the hottest thing since sliced bread. So I ran a few more Google Trends searches. So I did manage to reprove that cute animals still rule the internet. This yellow curve is the curve for golden retrievers. The red one is for pugs. As a proud pug owner myself, I was super excited to see the recent rapid rise of interest in pugs. Not quite as much as Docker, but still, it's cool. And then because, as the intro said, Civis has its origins in the political world, I had to run just one more search, which I think really puts all of this kind of into perspective. And depending on your point of view, it's either a fascinating exercise in electoral democracy or really scary for the future of the country. But that's all I'm going to say about that. So now that we kind of have seen this rapid growth of Docker, what are we going to do for the rest of this talk? So I really have 3 goals for the talk. So first, I want to try to answer this question of why would you use Docker for data science by telling you what Docker is and kind of what things it enables. and take this fatigued question like, oh man, do I really have to learn another tool? And answer it with what I think is a strong recommendation that, like, yes, Docker is worth your time to learn. And I'll partly do that by telling you some of how we use Docker for our work at Civis. And the back half of the talk is going to be a tutorial. So the second goal, like I said, is for you to be able to walk out of here kind of ready to use Docker. So we'll go through a tour of the Docker ecosystem, like all the tools that surround Docker, and then actually look at some code, Docker code syntax. And we're going to do this all through this, this real-life, end-to-end data science example. It's going to use Jupyter Notebooks, it's going to use Python, it's going to use R, it's going to use all the things that we know and love as data scientists, just kind of in the context of Docker. And you'll notice I have real life in quotes and air quotes here. And that gets at the third goal of my talk. And that is that I've tried to design the most hype-filled talk at Strata using our Google Search Trends data as an example. So what we're going to be doing for our tutorial example is deep learning for pug recognition with Docker with a Donald Trump cameo thrown in there. So watch out for that. OK, so let's start with what Docker is all about. So at its simplest essence, like Docker is basically a virtual machine. And you can think of it as providing you with a Linux operating system that's chock full and pre-installed with like all the software you need for running just like one particular task or application. Like you can think of it as, I have this laptop and it's built for a single purpose. I only use it for running this one program or this one application. So it's like other virtual machines that you may have used where you're running this guest operating system on top of your machine's host operating system. But there are a few big advantages to Docker. So Docker is what's known as operating system level virtualization. So what that means is that you're not actually running a whole separate operating system on top of your host operating system. There are features of the Linux kernel that kind of fake it for you. They give you these isolated bundles of resources. So CPU resources, file system resources, networking ports, all that sort of stuff that make it look like you have an isolated virtual machine. And that makes Docker images much more lightweight than traditional virtual machines. So this is the picture that you often see used to describe this. So on the left is a traditional virtual machine where you have your bare metal server down here. It's running some host operating system. And then you can run many different virtual machines, and each one gets its own copy, its own full copy of that operating system and the binaries and the libraries and everything. But with operating system level virtualization, things can be shared between containers but still act isolated. So in the Docker setup, you have your host operating system, and each running container can kind of share things from the underlying Linux kernel. They can share binaries and libraries if they're using the same binaries and libraries, et cetera. And that has a big advantage. So basically, Docker containers are really lightweight, and they're super, super fast to start up. So they start up in tens or hundreds of milliseconds rather than like a minute, like you might be booting up an operating system. And so if you want to think about it, it's not like on your Mac, booting between Windows and OS X in parallels where that can be kind of slow and a huge interruption to your workflow. It's kind of more like having a dozen laptops on your desk. Each one is on and ready for a particular purpose, and you're just kind of moving from one to the other. So it makes it really easy to work with a lot of different Docker containers. Second important thing to understand about Docker is that basically everything about an image is specified in this text file that's called a Docker file. And it's basically just a really light wrapper around Linux syntax for installing system packages and code and kind of anything that you could do on a Linux command line, except that it's encapsulated in this really nice to read text file that can be stored in GitHub alongside of your application. And the next big advantage is that Docker images are cross-platform, portable, and shareable. And there's like this whole system that's arisen for you to share Docker images with other people. So in particular, there's services like DockerHub and Amazon Container Registry that help you version and share Docker images with other people, basically in total analogy to what GitHub does for source code. And this will come up later for why I think Docker is really important for data science teams. So that's basically what Docker is at its essence. It's an isolated virtual machine that's for a single purpose that boots really quickly. So why would you want to use Docker as a data scientist? And I think there are a handful of reasons. The first big one is reproducibility. So by running all of your code inside of a Docker container, you can be sure that it's going to run exactly the same way every single time. Because the container's got the same operating system, the same version of all the system libraries, all of your Python or R packages, and it's got all of that exact same stuff, whether you're running it on your laptop, whether you're running it on some random Amazon server, in development mode, production mode. It's literally exactly the same thing. And if you're a data scientist, there's a lot of work in the research community on reproducible research. Jupyter Notebooks are an awesome way to do that. Our Markdown documents also an awesome way to do that. So embedding your graphs and your code and your text descriptions all in one document. And that's really great, but what about all of the system dependencies? Like, what about the operating system you ran the analysis on? What about all the system libraries? Like, you think all that stuff shouldn't matter, but 6 months later, 8 months later, when you come back, you can have your notebook and it just isn't going to run the same way. So Docker gives you a way to make it really, truly reproducible. By having your notebook and the Docker container that goes with it, you can kind of put those two pieces together and be certain that you're going to be able to reproduce your work. And on a related note, no one can mess up your cron job with Docker. So someone can't come along and change a version of a system package that totally breaks your cron job and you find out the next morning. If you're running it inside of a Docker container, that doesn't matter. As long as the container doesn't change, it's going to be doing the same thing. On a related note to reproducibility, there's documentation. So I was talking about this text file, Docker file description of what's in an image. So it's really clearly documented exactly what version of everything is in your container. And then the next reason I think Docker's great for data scientists is that as data scientists, we like to experiment. We like to experiment and we're polyglot. We use lots of different tools. So if you're using Docker containers for your work, it gives you this level of isolation that keeps you from breaking things. So if you're using Python 2 and Python 3, your setups aren't going to mess up each other. If you want to mess around with Anaconda, it's not going to mess with your system Python. You can link things against various different versions of linear algebra libraries. Your R setup isn't going to contaminate your Python setup, et cetera. I mean, I'm sure if I asked for a show of hands, at least several of us have managed to kind of brick a laptop by messing around with these kinds of things. With Docker, that's not going to happen. And that gets into this next point, that Docker really democratizes DevOps for people who are not infrastructure type people. So you can mess up, right? I can mess up a Docker file and mess up my running image, and it doesn't really have any repercussions, right? I just start over. It frees me to kind of experiment with things in a way that I can't do if I am just doing this stuff on an Amazon server. I can break the Amazon server, and there's a real cost to that. And it's very low risk for people like us who may be getting started with thinking about DevOps. Second big advantage, as I was saying earlier, is that Docker images are portable and shareable. So if you're a data scientist who is more about analytics and statistics and you're less into this DevOps systems type stuff, someone else can set up a container for you that has all of the exact dependencies you need, and they can push it to DockerHub, and then you can just work with it. You can just worry about your R or Python statistical code and not so much the systems stuff. And it makes it very easy for you to check out those images. There's a huge community that's arisen around Docker and composability, which I'll talk about in a second. So basically, if you want to use Jupyter Notebooks, the Jupyter folks have provided a set of Docker images that you can just go and grab from DockerHub. If you want to run an R Shiny server, you can go and get an official Docker container for R Shiny. So that's the community aspect. The composability aspect is that containers can be built off of other containers kind of in this layered fashion. So let's say I want to build an R Shiny app. I can start from the community-supported R Shiny image, and then I can just add my few things on top of it that I need for my particular thing. I can just add in the particular R packages I need for that analysis. So the composability means that you can just worry about the parts that are specific to your own workflow and let the experts take care of getting Jupyter running or getting Shiny running. And I think Docker really helps teams with communication. So if you are a data science team that has less technical folks on it, like I said earlier, you can set up images and share them with them, and they can just worry about running the code inside of those images, not taking care of servers. And if you interact with engineering teams, you can sort of treat Docker containers as black boxes. So you can set them up with everything chock full that you need for your R code or your Python code. And as long as there's a clearly documented interface, you can just give it over to production engineering teams, and they can just literally treat that as a black box. They don't have to know about how to set up the server. So you might be thinking, okay, this kind of sounds familiar to some things I get from AMIs, Amazon Machine Images, or Python virtual environments, and I think there's some important differences. So cross-platform and portable. So Amazon machine images are obviously not provider agnostic or cross-platform. You either have a Windows or a Linux one. You can't move your virtual environments from one platform to another or share them. Docker files are these transparent text file descriptions. AMIs sort of have that. Usually you log in and you do something to the image and then you take a snapshot, but there are tools like Packer that help you with that. And Python, it sort of has this text description. There's a requirements file that documents all the Python stuff, but it doesn't tell you anything about the system that you're running on. AMIs are shareable. Virtual environments are not shareable. Composability, yes, you can start with a base AMI and add your stuff on top of it, but there's no composability component to virtual environments. You can't just have a base Python 3 virtual environment and then add one thing to it for one application and another thing to it from another application. That doesn't work. There are community AMIs, but from what I've seen, really not the level of support that's already popped up around Docker. No community virtual environments. Multi-language, you can have a Docker container literally for any kind of application in any kind of language. Virtual environments are obviously Python specific. And then you can run a huge number of containers on one system. So I can have a dozen containers on my laptop and move from thing to thing. Obviously, you're linked to one Amazon machine image, but you could have virtual environments. So I think kind of taking all this together, there are lots of advantages to Docker over some of these tools that you may already be a little bit familiar about. So now let me kind of tell you how we manifest some of these advantages in our work at Civis. But I'll tell you just a little bit about who we are as a company first to help you understand that. So as the intro said, as a company, Civis traces its origins to the 2012 Obama re-election campaign, where a chunk of our staff were involved in the campaign's kind of groundbreaking analytics operation. So on the campaign, we did things like predictive modeling of voter behavior. We designed and ran large-scale field experiments, did all sorts of online fundraising, experimentation, and optimization. And since 2012, we've been taking a lot of those same techniques and moving them into the nonprofit world, other political campaigns, companies, and then increasingly kind of bundling them together as software as a service data science products that we've been selling. And I think because of that unique heritage, we employ kind of an interesting mix of people with different backgrounds. So this is some old data, but it basically shows the academic backgrounds of a bunch of our data science staff. So across some different departments, data acquisition, our data science team, our client-facing team, these are all people doing deep technical data science work, statistical analysis. But we have basically as many people from kind of CS, hard math, hard sciences backgrounds as we do from social science, political science, that whole world. And so those people might be writing code, but they have less of the kind of DevOps type background. And as a company, we're really trying to inhabit this sweet spot in the middle of the traditional data science Venn diagram, but with our own little sector added on there for social science methodology. So things like randomized controlled experiments, survey design, causal inference from observational data, that sort of stuff. And so you need people with lots of different backgrounds to do something like that. So how do we actually use Docker, some of the features that I mentioned? So first of all, our data science team maintains this very large set of Docker images, both for different production applications, but then also for interactive use by less technical analytics folks at the company. So we have a Docker image for doing our predictive modeling software. We have a Docker image for Bayesian time series modeling and aggregating polls together, kind of Nate Silver style. We have a Docker image for Bayesian analysis of randomized controlled experiments, processing surveys, various Shiny apps. And then general purpose images just for I want to do some R coding. Give me an image that's chock full of all the R packages I need, or same thing with Python. And so we maintain those images because we know a little bit more about DevOps than some other folks. But with basically just some training in Docker, so how to run Docker on your Mac or on your Windows laptop, our less technical client-facing folks can pull those images down from DockerHub and then just run all of the code that we provide for them in there. They can make pull requests and change the actual statistical and analysis code without really having to worry about the DevOps piece of it. And if they are interested in learning a little bit about the DevOps, looking at the Docker file and making pull requests against that is a really approachable way for them to start by just adding a new package or modifying the version of something. It's not as intimidating as going onto the server and sudo doing some stuff. And then we, like I said earlier, pass over a bunch of images to our engineering team as sort of black boxes with clear interfaces. So they can hook up a front-end button that basically does some really complex data science just by knowing the interface of that Docker container and without having to know anything about the R or the Python that goes into it. And I think another really interesting thing that we've done is developed this batch cluster computing solution that we use really heavily for our internal work, but we've now started to give externally to some clients. So it's basically an auto-scaling cluster solution. So if it gets busy, it just boots up more Amazon nodes. But from a user's perspective, what you do is you specify two things. You specify a Docker image with which to run your code, and then you can specify either just a command to run in that image or a GitHub repo that has your code in it, and it sort of puts those two things together. It runs them, and it passes you back all of your log output. And our internal folks can just run these things with a simple web form. They can hit it via an API. But it really allows less technical people to scale up the work that they do just by using this kind of community set of Docker containers and not having to worry about the servers that they're running things on. OK, so now I want to transition into the kind of back half of this talk where we're going to talk about the Docker ecosystem and what the tools actually look like so that you can hopefully walk out of here with some really concrete new knowledge. So let's talk about the Docker toolchain. So the first basic component of using Docker is the Docker daemon, also sometimes called the Docker engine, and the Docker client. So Docker has like a server-client architecture. So the Docker daemon has to be running on any machine if you want to do Docker. And then the Docker command line client connects to it and tells it to do some stuff. So you're going to be doing things like Docker run, Docker build, et cetera, kind of like the Git system where you have Git and then a subcommand. Second thing that's important to know is a tool called Docker Machine. So Docker Machine helps you to get a server up and running and configure Docker on top of it. So, and it allows you to point the client at that running machine. So to use Docker, you have to have a Linux machine running. It needs a Linux kernel, which you don't have on your Mac laptop. But with Docker Machine, you can create a local VirtualBox VM that's running Linux, and then you can point your Docker client at it. We'll see how to do that later. And then you just run Docker commands, and it's just like being on a Linux machine, but behind the scenes, it's communicating with that VirtualBox virtual machine. Docker Machine will also provision servers for you on Amazon, DigitalOcean, other kinds of things, and then you can run Docker commands locally on your laptop, but it's actually doing stuff on that server in the cloud. Next important component that I mentioned earlier is DockerHub. So I think they've done a really awesome job with DockerHub, basically just building an incomplete analogy with GitHub. So DockerHub is to Docker like GitHub is to Git. And it's basically an image registry with a nice front end. You can push your images there. You can see the versions. You can add descriptions. You can share them. Other people can pull those images down from DockerHub. It's really the way to share Docker images and to get access to the community images. Then there's Kitematic. So Kitematic used to be a standalone company that got merged into Docker. And it's a really simple graphical interface for launching and using containers. So it's a great place to start for less technical folks or less technical colleagues if they're not into doing stuff on the command line. Then we start to get into things that are maybe a little less common to use if you're a data scientist. So there's Docker Swarm. Docker Swarm helps you to boot up a cluster of machines that are running Docker, and then you can launch and schedule containers on top of them. So here, think about like if you're running a web application and you want to boot up like 20 servers and launch multiple instances of it and do some kind of like load balancing. That is what Docker Swarm is for. Docker Compose may be something you would run into, which is a tool for helping you define and run multi-container applications. So basically, inside this simple YAML file, which we'll see an example of later, you specify all the different containers, which images they are, and how to link them together. So maybe you have a front end that's running in one container. You have an API that's running in another container. You have a database that's running in another container. It allows you to separate and isolate all those things and then connect them together. And Docker Compose used to be called Fig. It was also, if you've heard of that, it was also a standalone tool that got merged into Docker. I think at some point Docker realized that this was super confusing and there are like 10,000 tools. So they launched Docker Toolbox, which was yet another tool you had to figure out. But it basically bundles all that stuff into a single installer that you just install Docker Toolbox and it gives you all the things that I just mentioned. And then as of last week, hot off the presses, they released yet another tool in beta mode called Docker for Mac and Docker for Windows, which is meant to supersede Docker Toolbox. It is basically just the all-in-one installer that gives you like a native Mac experience for working with Docker and a native Windows experience. And that should simplify some stuff and just make it nicer to work with. OK, so now I want to launch into the kind of tutorial example piece of it. And if you're interested, all of this code is up on GitHub. Take a look at it with it has links to the Docker files, but also links to the Docker images on GitHub. So you should actually be able to literally reproduce everything I'm about to show you with the Docker containers and the commands that are up there. That's the whole idea of Docker, after all. So if you try it and you cannot get that to work, you have like a money-back guarantee from me. I haven't cleared that with O'Reilly yet, so I don't know. We'll see. So what is this application that we're gonna look at? So here's a screenshot, and actually I'll just start this demo running and talk over it. So basically we're gonna make an R Shiny application. Shiny is a really nice front end framework for R, and it's gonna let the user stick a URL in there, and then once the URL is in there, it grabs the image from the internet, it crops it and shrinks it down to the size that we need, and then it makes an API call. And that API call goes to a second container that we have running. And that second container is serving a model that we built in Python, so a neural network model, that is supposed to recognize pugs versus golden retrievers. And you can see at the bottom, these are test images I just grabbed off of Google Image Search. It's doing a really great job. It's unhappy that that's a pug. It's unhappy that that's a golden retriever. It was pretty happy that this is a pug. So it takes the model score back from that container, and then it displays this nice message for you. And all of this is linked together and booted up using Docker Compose, which we will show in a second. I'll just let this loop through to the end. So it thinks with 97% certainty that this photo of Donald Trump is actually a pug. I think actually if you kind of look at that expression on his face, it really makes sense. So, all right. So how is something, I know you have to be thinking, right? How is something this awesome possible? So let me kind of walk you through all the pieces of Docker that I used to build that application. So first, it starts with Docker Machine, which I was saying is the way that you boot up servers to run Docker. So first, I started by booting a local VirtualBox machine to work locally on my Mac. And then once I realized that I was having memory issues, I used Docker Machine to boot up in exactly the same way a server on Amazon, and then eventually a GPU instance on Amazon. So Docker Machine handles booting those three things and then pointing your Docker client at it. And then I started by doing the work in a first container, which is like a Python container. So I started from the Jupyter community image that has the notebook just up and running, and installed on top of it Keras, which is a deep learning package in Python, if you know it. And then worked inside the browser, which is running in the container, just literally exactly like you work with a notebook on your laptop. There's no difference from the interactive standpoint. And what we're doing here is a form of transfer learning. I took a pre-trained ImageNet network, convolutional network, chopped off the last layer, and then just presented it with images of pugs and golden retrievers and had it learn that last layer for our particular pug recognition task. The regular network actually did a great job knowing that it was a dog, but it didn't go that really crucial last step and tell you that it's a pug. So once the model's built in the notebook, I took advantage of composability, and I started from this image that was already set up to do our Python stuff, and just added one more thing to it, which is Flask, that allows us to serve the model with an API. Then in a totally separate container, we defined the R Shiny application, and then used Docker Compose to link the two of them together and start the application running. So let's look at some of the syntax for how this actually works. So here's what Docker Machine looks like. You say Docker Machine, create me a machine, and then you kind of tell it what kind. So here I'm creating a local VirtualBox machine, and I give it a name just like my VM. And then once I've done that, the second line tells Docker to point its environment at that machine. So then when you're using Docker commands, it's actually running them on that VirtualBox machine that's running on my laptop. If you wanted to boot up a server on Amazon, it's essentially exactly the same thing. You say Docker Machine, create me a machine, except use the driver for Amazon, and then you pass it your Amazon keys, and you tell it what kind of instance you want. And then again, you point your Docker environment to that machine, and anything you do is going to happen on that Amazon instance. So I talked about the Docker file, this text description, and here's the actual Docker file that I start with. So we start from this Jupyter community image that has the notebook in it. And then I run a bunch of commands that look like Linux commands. So pip install is installing these packages on top of that image, install Keras and some other stuff. And then I'm running some Linux apt-get commands to install ImageMagick, which is just like an image processing thing. And then So then I said earlier that once we define the model, we use composability to just add a couple things on top of that image. So here, we're starting from the base image that I just defined, and now just adding a couple more things on top of that for our API. We add Flask, we copy over the model weights files that we stored. Expose tells the container to open up a port, so we're going to serve our API on port 5000. And then this last bit down here says when the container starts, what command should it be running? It should be running this command that actually starts the Flask API. So just a very lightweight wrapper around Linux commands. And now we'll see what it actually looks like to build this image. So Docker has a very similar syntax to Git, where it's Docker, a subcommand, et cetera, and it's very easy to get help just with that flag. And to build an image, by building an image, I mean taking that text description from the Docker file and turning it into an image that you can run or push to DockerHub or whatever. So you just say Docker build, and I want to tag it with this. So this is my DockerHub username, and then the name of the image, which is my pug classifier notebook. I point it to the Docker file and then the local directory context. And when it's done, I can run the Docker images command, and it will show me all the images that I have access to. So here's a screen capture of it running. It'll go by kind of quickly, but you can see it's basically going step by step, and it's running each one of those commands in the container produced by the previous command. And so you could see maybe some pip installs scrolling by. Right now it's doing like apt-get update and apt-get installing a package. And then it went by really quickly at the end, if you could see it there, but I ran Docker images, and it now told me that I had an image available called pug classifier notebook. Now that I've built that locally, I can push it up to DockerHub, just like Git. I can say Docker push, and then this image name, and then it will appear under my account on DockerHub here. So here's my username, here's the notebook, or sorry, the name of the image, and then I put some kind of text descriptions and a link to the Docker file in that flexible field. And if you wanted to go use it, you could just do Docker pull, mdgost pug classifier, and you would have that that image locally to work with. So what does it look like to actually run the container? So here's an example of running an interactive container. So you say Docker run. This -it says I want to interact directly with this container on the command line. I tell it the container to run and the command to run inside of it. So here I'm just running the bash command, which will just open up a command prompt inside the container for me to do things with. But if you didn't want to run interactively, you just wanted to leave the container running in the background, doing its thing, having its ports open, you can say Docker run -d, which tells it to run in daemon mode. You can map the ports from the container to your local machine, and then tell it the image name. So here, the Jupyter Notebook image is set up to run the notebook as soon as you start running it. So what that actually looks like is I ran that command, and you can see it basically just returned instantly. The machine has started up, and then I go into my browser, and I type the Jupyter address, and here I am inside of the notebook, doing whatever I want in the notebook. So I'll let that run one more time, so you can see starting up the container is instantaneous, right? And then from this point, you're just in Jupyter. You don't know that you're in the container, except that it's frozen your dependencies, and you know now, 6 months from now, if you start that container and run your notebook in it, it's going to have exactly the right stuff. You can also mount volumes inside of a container, which is a great thing to do for debugging. So in this syntax here, what this says is start this container and mount a volume. And here I'm going to take a local directory on my machine, and I'm going to make it appear in this certain spot inside the container. And so if you're working on some code, you can mount that code into your container, and it will run inside the container, but then any changes you make will be reflected back and forth. You don't have to keep rebuilding the image and putting the file in there. You can just sort of sync it back and forth. And you can also inject environment variables into the container like so. You can, with this --n flag, so I can run this container, and then now inside the container, I will have these environment variables that are available to me. So I can set a database user and a database password without having to store that inside of the Docker image that other people might be able to pull down from DockerHub, or store that in GitHub somewhere. Okay, so those are the basics of like what's a Docker file look like, how do you build it, how do you run it, kind of a lightning introduction. And now let me just show you Docker Compose, which I used to actually like run that application. So I said before there are two pieces to the application. There's the R Shiny server front end. I didn't show you the Docker file for that, but you can just trust me. And then there's the Flask API component. And so we name the two pieces and we tell them what images should I run in each container. So in one, I'm going to run this Pug classifier Shiny image that's just got the front end, and in the other, I'm going to run the Flask API. I specify if either one should open up some ports, and then this link part is really the magic part. So here I'm saying, hey, my Shiny server container, it's going to need to access the Flask API container. So I just tell it to link the two containers together, and it sort of just does that magically. And then you run Docker Compose up, and it's going to take care of starting those containers and then linking the two of them together. So here I'm running Docker Compose up, and it's saying it's creating the Shiny container, it's creating the Flask container, and then it's going to start showing me the logs. So these are the logs from the Flask API starting up and just being ready to serve the model scores. And that's basically it. And here's what what the app looks like when it's running. So the super cool thing about this is that once you've done that, like once this is working, I can use, and you can use Docker Machine to just boot you up an Amazon server. Say, Docker Machine, give me an Amazon server, and point Docker at it. And like we saw in that first slide, and then you can run Docker Compose again, and it will actually just boot up your containers, link them together on your Amazon instance. So it's like total seamless deployment from the thing that was working locally on your laptop with just like one more command, you push it up to an Amazon server, and now it's like live somewhere for people to use. Okay, actually that's perfect. I think I have about 5 minutes left. So that's really all I wanted to talk through with you guys. Hopefully I've given you a sense of like what Docker is all about, why people are so excited about it, and I think why it's really useful for us as data scientists. And then hopefully, again, enough of a flavor of like what the syntax is like that if you're really interested, you can walk out of here and just kind of start using Docker. And a great place to start is just by grabbing the code from this, from my GitHub link and trying to just reproduce some of the stuff that I just walked you through. And yeah, perfect. I have about 5 minutes, I think, for questions if there are any. Oh, if you have questions, if you can go up to the microphone. All right, I can repeat it. Go ahead.
At the very end, do you actually have 3 instances or 3 Docker containers running at the same time, or is it just one container that will be taking all those resources that you just specified?
It's 2 containers running at the same time. So it's one container that's running the Shiny front end stuff, and then it's a second container that is serving the model API. Sorry if I can just get back to this. So it's just these 2 containers. It's the Shiny front end, which makes API calls to this, which is serving the model scores. This third container, it's just this container is built from this container. So it starts with everything in there, and it just adds one more thing. But it's only these 2 that are running, if that makes sense. Yeah, OK.
Another question, Jupyter Notebook needs a web browser. Is that something you already added to Docker at the time?
So,
advantage of what's on your other machine outside of the
so the question was about Jupyter Notebooks needing a web browser to run. So the web browser that you need to connect to the notebook is actually on your local laptop. And it's going out and connecting to the thing that's running the Jupyter server. So if so normally when you start Jupyter, like on your laptop, you just go into a terminal and you start it, and then you go to your browser, and your browser is talking via API to the server. So here, it's exactly the same thing, except the server is running in a Docker container, either locally, or if it's running on Amazon, then you just point your local browser to that Amazon IP. To create containers, do you need to have any special permissions? Yeah, that's a great question. So there are some, I have to remember this. So usually you need like sudo access to run Docker. So like if you install Docker yourself, like freshly, you have to preface all those Docker commands with like sudo docker, whatever. I'm pretty sure though with Docker Machine, it just works. So if you use Docker Machine to make your to make your virtual machine or to make your thing on Amazon, you don't need to preface everything with sudo. It probably like runs as some user that is added to the Docker group. Yeah. Yeah, so the question was, I understand that you can attach data to containers. So there's like a concept of a data container or a data volume. So that's not something I've used personally, but you are right. Like the idea is that like if you were running like a database, let's say, if you want to run like a SQLite database, you need to have that data stored somewhere. And the right way to do this in Docker land is to store that in its own container. But I don't personally have experience with that. So in the back. Yeah, so the question was if I have any experience using things like Vagrant or Ansible, and if I can comment on the differences. So I have not used Ansible. Our DevOps team at Civis uses Ansible. I have used Vagrant, and actually in a previous job, I set up basically the same thing, so a Vagrant image for serving Shiny for applications. And my experience with Docker is it's like for me personally, it's like night and day. So I think the Docker file syntax is just way easier than, so if you don't, Vagrant is another a system for managing virtual machines. And like if I remember right, the syntax is Ruby, which I'm not like natively familiar with. And it was just a lot harder to figure out what's going on. But the Docker file is literally just like running commands on the command line. So, and then also like there was already a Shiny image for me that wasn't there for Vagrant. So I think personally, I vastly prefer Docker to either of those two things. In the far back, yeah.
Once you put it up on Amazon, can you change the URL so it has like a nice name, divisibug.com?
So the question was like once you push your running application up to Amazon, can you point that at a different URL? Like, is this a pug.com or something? And the answer is definitely yes. I'm not 100% sure how you would do that, but like, you'd probably have to go into the Amazon console and like do some mapping between like with like Amazon DNS features. There's definitely a way to do that, but like that's I think outside of the Docker world. I don't know how we're doing. No? Can I take one more? All right. Yeah. So the question was when. Yeah, so the question was how much CPU and memory does the running container use? Are there requirements and stuff like that? So you can control that. So you can with some of the Docker run command line options, you can tell it don't use more than this CPU. I'm going to limit it to this much RAM. And actually, our internal thing that I mentioned has like the user can specify don't use more than this much, more than these resources. I don't know what the default is. Probably by default it will get everything. It will have access to as much as you have available, but you can place limits on it. Okay, great. Thank you, everybody.